Welcome everyone to Math 111. This is our final section, section 4.5. Excuse me, 4.6. Woohoo! All right, let's take a look. All right, so this is modeling exponential growth and exponential decay. All right, so let's take a look at what it says. An exponential function, which we know is in the form of some constant times a base raised to a variable, where c is greater than 0 and a is greater than 1, is exponential growth. If a is between 0 and 1, then you end up with exponential decay. And if you think about why that would be, it's simply like if you're taking a, let's say if a is 2. If I go 2 to the first, look, that's 2, and I go up, I'm growing. But if a is 1/2, then 1/2 to the first, 1/2 times 1/2 is 1/4. And you can see I am not growing, I am getting smaller. So we would call that decay, right? So here are the graphs, exponential growth and exponential decay. All right, so let's take a look at this. It takes 29 years for the initial amount of, how would you say that? Strontium 90? No idea. To break down into half the initial amount. That is called the half-life, 29 years. Given the initial amount of this substance, find an exponential decay model that gives that at time greater than 0. Okay? So let's take a look. So we know that if I have an initial amount, so our general model that they gave us looks like this. And we know that we have twice that amount. I'm sorry, 1/2 that amount, half that amount. We're not doubling, we are having. When t is 29 years. So I can use this to solve for k. So because when I divide both sides by the initial amount, this is going to cancel. We're going to have this equation. So now I'm going to take the natural log of both sides. Those are going to cancel their inverse functions. Now I'm going to divide both sides by 29. Okay, so we have this. And now we're going to take k is equal to negative 0.0239. I want to take a second to just say that it makes sense that this is negative. E is not a base between 0 and 1, but if I make it a negative k, then that makes it 1 over e to the 0.0239, which is a number between 0 and 1, which provides it to make it into that decay. So my model that they're asking for would be a of t equals a naught e to the negative 0.0239 t. All right? All right, now it says calculate the time required for it to decay to 1/10 of a naught. So 1/10 equals, if I don't need the a naught because I'm just going to divide it off both sides, e to the negative 0.0239 t. And I'm just going to divide both sides. I'm going to take 1/10 and divide it by that e to the negative. No, I'm not. Sorry. this is raised to the power of t, so I need to take the natural log of both sides. So I take the natural log of 1/10, the natural log of e to the negative 0.0239t, divide both sides by negative 0.0239, and that will give me my time. So I need the natural log of 1/10, and divide that by our constant, negative 0.0239. And it will take 96 years. Now, let's just use like a little reality check if we want to. Its half-life is 29 years, so it's half at 29 years. At 58 years, it would be at a quarter then. Then another 29 years is 87 years. It would be at an eighth. And another 29 years at 116 years, it would be at 1/16. So our answer of 96 years does kind of fit right into what we would like understand to be true, because 1/10 is between these two numbers, and 96 is between 87 and 116. So we have the same problem here with half-life of 6 years. We're going to take the same kind of idea. 1/2 equals e to the k times 6. I'm going to solve for k. So the natural log of 1/2 equals k times 6. Taking the natural log of both sides, divide both sides by 6. So I do that. Sadly, I left my calculator on my desk at work, and I miss it. So k equals, I'm using a calculator on my phone, and I find it much more difficult to use. And so that would be our model. A sub t equals the initial amount we have times e to the negative 0.11524 times t. All right, population growth. We have this function in the form of some constant which models the population growth. We want to find what our constant number is for this. It says it is expected to grow from 220 million in 2000 to 335 million in 2020. So we're going to use our years after 2000. So let's talk about our initial value when t is 0. When we have 2000 as 0 years, we have 228 million. So our c is going to be 282 million. And we're in millions, so we're going to say c is 282. Because if that c is 282, then we have our model. When I put a 0 in here, that makes this whole thing 0. E to the 0 is 1, and that leaves me with 282. And now we want to solve for k if we're expected to have 335 million, e to the k in 20 years, from 2000 to 2020. So we're going to solve this model here. And we can verify how good this model is since we are looking at a past model. So we're going to take, divide both sides by 282 first. And then we're going to take the natural log of both sides. That u will cancel when you take the inverse. That's why we took the natural log. And divide both sides by 20. And we get r constant equals, plug this into this calculator, see if it can handle it. And k equals 0.008611. Right. So our model is a sub t equals 282 e to the 0.0086 t. Says, what would we expect in 2016? I'm going to put a 16 here. So I'm going to say a to the t is 282 e to the 0.0086 times 16. I still have that full digits in my calculator right here, so I'm just going to times that by 16. And I'm going to take e to that answer. I don't know how to do that on this calculator, but that answer is, so I'll just type it in. Oh, we got it, we're good. And then we're going to times that by 282. And we're going to expect in 2016 we'll have 323.6 million. 0.7 rounding to the nearest tenth. All right. Estimate the population 2015. Same idea. You're just going to take that, put 15 into our model. So 282 times e to the try this one more time. It really is a demonstration of how important it is. You're very comfortable with the calculator you're using, especially when you take it in for an exam. Really saves you a lot of time. And clearly did something wrong there. Oh, because I typed in 228 instead of 282. Let's try that one more time, and we'll get an answer here. I can't stress enough how important it is that you're comfortable with the calculator you're using. Have some practice with it. So this sounds right, 3. And that I rounded to the nearest fourth, or to the nearest 10,000ths on this, on the decimal for the exponential, which can make a pretty significant difference. So, right, growth of the national debt, kind of the same idea. It says table 1 shows, so there's a table that's missing here that's in your text that you can take a look at. And you can plot those points, like something like this, right? And then, so kind of the way that we do this when we're not like using technology to find that equation for us is you're going to just kind of graph in kind of what you think is the best fit, pick 2 points, and then from there you can solve like we did in the past chapters, in the past section. So, if you have these 2 points here that seem to be good representations of your scatter plot, like you're looking at numbers to kind of equal above and below, then you can use that to build your model. Okay, so basically all these problems, you kind of run through the same process. You pick 2 points on your graph. You solve for C. That's always going to be your initial point, right? Initial value when T is 0. And then you solve for K. If you have a value for T, they'll give you a value for T. And they'll tell you that it's equal to some value at T. And so then you solve for the K. And then you rebuild your model so that it is your initial value, the K that you solve for, and T is your variable. It's a lot like when you were in Algebra 1 and you were like solving for mx plus b. They gave you 2 points and you would solve for b, and then you'd rewrite the equation with the b that you solved for. It's the same idea here. We're just taking the 2 points, solving for k, and then rewriting it so that we have a value for our constant. That works for our model. All right, hope this helps, and I hope you guys all have a great weekend. Good luck on finals.